So I will be talking today about Swift hardware hacking. Yeah, so I'm Sally Shepard. I work at hotels.com, where I'm a technology manager there. We're hiring. Come talk to me if you're looking for an iOS role in London. I'm also a student. I'm currently doing a master's degree in the Internet of Things. Who knew you could get a degree in the Internet of Things? Why would somebody do that? Especially since my background is in iOS. I did Objective-C before, so why would I want to do Internet of Things? Well, I've always really enjoyed making stuff, like building things, and there's something quite special about making physical products. And over the years, I've done a lot of small electronics projects that seem to have a slight recurring theme of involving my cat. The one on the right is a cat bed made out of an old iMac. And it basically sends a tweet when the cat has been in the bed for more than 5 minutes, letting the Twitterverse know that he is taking a nap. And the one on the left is actually what I will be doing my dissertation on, which I like to call the Internet of Things for Cats, which is like a fitness tracker and kind of health platform for cats. So as my background is in iOS, I write mostly Swift, but the degree I'm doing is all in Java and Python. Not pleasant. It's not too bad. I'm not bashing them. Code of conduct. But I do prefer Swift, sorry. I don't want to offend anybody. So I asked my lecturers, because I am actually the only student on this degree. Yes, all the lectures are just me and the lecturer. It's very difficult. It's a lot of focusing. So I asked if I could do it in Swift, and they agreed because, well, I kind of get to do whatever I want on the course. So one of the projects I've done was something that I've called the First Local Cat Savings Bank, and it's a IoT project written in Swift. And I wanted to go through it mostly to show you that hardware isn't as scary as you might think it is, and that hopefully it will inspire you to try something yourself. So let's start by looking at the actual product. So I didn't make this thing. This is an existing thing. You can buy it on Amazon. But this is kind of part of what First Local Cat Savings Bank is based on. So this is the original savings account. The user puts their deposit on the platter, the cat comes up, takes the coin, the money is deposited into the savings account. So customers have loved this. This has, I don't even know how many 5-star reviews on Amazon, but a lot. But we've also gotten some feedback from our customers. They want something smarter. The savings account doesn't let customers know how many coins are in their account or what the value is. And if you want to count all the money, you have to take it out, count all the coins. There's lots of human error involved, and you have to physically be there with the account. So we've listened to our customers, and we've come up with a new product called the Smart Deposit Platform. And we've designed this to solve the friction points for our customers. So let's take a look at how it works. So the savings account sits on top of the new Smart Deposit Platform. The user, like before, puts the deposit on top. The cat comes up. The cat takes the money into the account. And now the Smart Deposit Platform says, you've deposited 20 pence. And then it updates the balance. Yes, it updates the balance with the new deposit. And then finally, the deposit information in account is viewable on the iOS app. But what's actually powering this? Like, how does this work? So there's kind of 3 parts to it. There's the Smart Deposit Platform, the cloud, and the iOS app. So as the user makes the deposit to their savings account, the Smart Deposit Platform calculates the value of their deposit. And once the value is calculated, the deposit information is uploaded, which is where the cloud comes in. So this maintains the customer's account, the deposit information, the account overview. Now our banking platform is based on Swift. The physical hardware is powered by a Raspberry Pi. The cloud is powered, well, Katura for server side, which is Swift, and obviously our iOS app is Swift as well. Obligatory cat GIFs. I'm amazed I made it this far. So let's look at how we actually build this step by step. So the first thing we need to do is set up our development environment. So I mentioned that the Smart Deposit platform is powered by Raspberry Pi, but you might be wondering, what does that mean? Because you might not know what a Raspberry Pi is. So a Raspberry Pi, pictured here, is much smaller in real life, which is why there's measurements there. It's not that big. It's a very small computer which runs Linux, and there's many different distributions and versions of Linux you can put on it. The kind of officially supported recommended one is Raspbian, which is the one that I use. I haven't really ventured out and tried other ones, but there are other ones. The Raspberry Pi is quite cool because it is basically a computer. You can plug a monitor in, keyboard, mouse, Ethernet, audio, everything. And it supports Swift. And it has these cool things called GPIO pins. And these let us connect to components like actuators and sensors, where we can actually do cool hardware things. And then it also has Bluetooth LE, because in the IoT world, Bluetooth is generally a good thing to have for talking to other bits. So the GPIO pins, GPIO stands for General Purpose Input Output. And these are the pins that we use to talk to components. So on the left is kind of a blown up picture of where the pins are on the Raspberry Pi. And on the right, sometimes when you're building circuits and they get a little bit more complicated, it's pretty hard to work directly with the pins on the Raspberry Pi. So you can get these nice little breakout boards that you can connect to a breadboard, and then you just plug wires in. There's no soldering. It's all very, very calm. And these pins do a lot of different things. So the one that I've been using, the Raspberry Pi I've been using for the project is a 3B+. And so this is just an overview of what the pins do. You don't need to memorize it. There won't be a test later. Some of them supply power, some of them are ground, and the rest of them are kind of pins that we can communicate with. And each pin we can either set as an input, so we can read stuff in from it, or it's an output where we're sending information to it. Now, for most of us, if we want to use Swift, we would install Xcode. And although Xcode for Linux was at the top of my WWC wish list this year, Apple was busy doing many other things, which is cool. But yes, there is no Xcode for Linux. So how do we actually access Swift? There's a lovely community of people, the Swift for ARM community, who make it possible to very easily install Swift on a Raspberry Pi. So first you run the curl command, and then you just do sudo apt install, and then the version of Swift. So I think the currently supported version of Swift is 5.0.1. But yeah, they are pretty quick about adding support. The package is about 120 megabytes, so depending on how your internet connection is, it's pretty quick to actually install it on the Raspberry Pi. Back at, a few years ago, before this existed, you used to have to do it yourself, and on a Raspberry Pi that could take a day. So this is amazing and wonderful. Okay, so once we have Swift installed, then we can create a new project. So we'll run, once we kind of have the directory where we want to work, we'll run Swift package init ---- type executable, and that will generate the following files and folder structure. So we'll get things like main.swift and package.swift. Yay, Swift package manager. Cool. So before we look too deeply at the components that we'll be using, we need to be able to actually communicate with these components using Swift. So we're going to use a library called Swifty GPIO. So to do this, we'll add it into our dependency. We'll add the dependency into our package.swift file. And then we'll be ready to start talking to these pins with Swift. Now, just a quick note on Swifty GPIO, you're not limited to just working with a Raspberry Pi. It supports like all sorts of different Raspberry Pis, Beagle Bones, Orange Pis, Tinkerboards, chips, banana pies, all sorts of pies. Anything basically ARM related, and that supports like Raspbian, Ubuntu, or Debian. Cool. So when I was developing this, I personally like to do all of my development on a Raspberry Pi. So I plug a monitor into it and a keyboard and a mouse, and I use it as a computer. I use an IDE on the Raspberry Pi. Other people, which is cool, like to use stuff more like on their Mac. So they'll either write their code on a Mac in like Xcode and then just pull it onto the Raspberry Pi. It's easier. I like to be difficult. You can also run the Raspberry Pi headless, which is basically when you SSH into the Raspberry Pi from like your Mac, and then you can use the Mac to kind of control the Raspberry Pi. It's up to you. But yes. Okay. So now that we have our Raspberry Pi ready with Swift, and we can talk to the pins, we'll start digging into how to make the hardware actually work in the Smart Deposit platform. And the first thing we'll look at is showing the deposit status. So for this, we'll be using the very memorably named HD44780. Yes, electronics have like it's all just letters and numbers for the most part. So it can be kind of confusing sometimes. But this is basically a 16 by 2 LCD display. On the left is a picture of the actual component. And then on the right is the kind of basic wiring diagram, so it shows which pins on the HD44780 need to be hooked up to what pins on the Raspberry Pi. So basically, this is what it looks like when I wired it up. So I'm by no means saying that I'm like an electronics expert. This works. It's not beautiful, but it does work. And it is basically as simple as just plugging things into holes in a breadboard. Like, you don't need to know huge amounts about electronics to make this work. Congratulations, you've made it 33 slides without seeing any Swift code. So here, now we have some code. And this is what we'll use to basically talk to the LCD screen. So first we import Swifty GPIO and the HD44780 LCD. Then we're going to set up Swifty GPIO to tell it what type of Pi we're using. There's a bunch of pin setup code, and then we create the LCD with the pins that we'll be using. We clear the screen, move the cursor, and then we print the string. It's beautiful. So the code shouldn't be too intimidating, I hope. It's pretty straightforward. I wouldn't exactly call it elegant, but it works. Cool. So we've been able to write some characters out to the LCD screen, but now we want to know what coin the customer is actually depositing, so we know what to put on the screen. So we'll be doing this by calculating the difference in weight between the previous deposit and the current deposit. And this difference is what will give us the weight of the coin. So for example, we've got our current savings account, so we take that and then we subtract the previous one. So maybe currently it weighs 1,003.5 grams, but previously it was 994 grams. That would give us a difference of 9.5 grams, and that is what a 1 pound coin weighs. Cool. How do we weigh something? To weigh something, we're going to use something called a load cell. So on the left, this is a picture of the load cell component. On the right is my cat, very helpfully testing out my implementation of a load cell, which is sandwiched in between two pieces of an IKEA cutting board, because prototyping. And the way a load cell works is basically you put a weight on top of it, and this is exaggerated, but you put a weight on top of it and it bends. And inside the load cell are a bunch of small wires. So when it bends, the small wires inside also bend. And this bend in the wires causes a change in resistance. So the heavier the object is, the more the wires bend, the more resistance there is, so the heavier the thing is. So this change in resistance Like, we don't plug the load cell directly into the Raspberry Pi because the signal isn't like usable at that point. We need to use an analog to digital converter because the Raspberry Pi actually only works with digital signal. So this little analog to digital converter is an HX711, and it's designed specifically to work with load cells. Now, we have to figure out how to actually use this because it's not supported directly out of the box with Swifty GPIO. So we're going to look through the data sheets. The data sheets are a really crucial part in building circuits and working with electronics. They're like the instruction manual for components. They explain what it does and how to use it. They list things like features, specifications, block diagrams, pin descriptions, assembly code. And I apologize for showing you C code, but it also has sample C code for the reference driver. And this explains what we need to do to be able to get values from the HX711. And in essence, this is doing something called bit banging. And this is basically where we'll be using software to directly set and sample the state of the pins to get a usable value from it. So hopefully that doesn't sound too intimidating. But yes, so the Raspberry Pi, the GPIO pins handle digital signal. So digital signal is either a 1 or a 0. Whereas an analog signal could be lots of different things, right? So if we were reading something like a weight, we probably don't just want a 1 or a 0. We want an actual number, like 140 or 768. So how would we get these values through a digital signal? We can look at the binary representation of these numbers, and then we have the numbers in a form where they're entirely made up of 1s and 0s. So that's helpful. But we can only send one number at a time. So it's not quite going to work unless we actually agree on a word length between the two, between the component and the software that we've written. So in this example, this is 12 bits long, because there's 12 1s and 0s. And when we have this agreed word length, we know when we have the full value. So in this line in the C code, we can see that we're looping through 24 times. So we could probably assume that our word length is 24 bits. And there is a bit in the data sheet that does say that it's 24 bits, but it's more fun to look at code. Not C code, but not bashing C. So inside the for loop, the next thing we're doing is we get 1 bit in. And we do this by actually pulsing the clock on. So we send a signal out to the clock to say on, and then it sends us a bit back, and then we pulse the clock off. And then we shift everything over until we have a full 24-bit word. And then at the end, we run into this line, which looks a little strange. But if we go back to the data sheet, there is actually a little bit that specifies that the output that it provides is in 2's complement format. So again, not something that we normally work with in Swift. But 2's complement enables us to represent negative numbers as well as positive numbers in binary. So we basically look at the first bit of the 24-bit number, and if it's a 0, then that means it's a positive number. If it's a 1, that means it's a negative number, and we need to flip all the bits to get the actual negative number. So don't worry. Usually weights should be positive when we're weighing things, but sometimes before you've calibrated the scale, you might have negative numbers to deal with as well. Cool. More code. Okay. So here we're just setting up the pins for the data and the serial clock and setting the direction, so either in or out. And then we've got kind of side by side the Swift code and the C code. So very simply looping through 24 times, getting a bit in, constructing the number, and then using 2's complement to flip it if it's negative. Okay, hopefully not too scary. It should be pretty simple. And then, of course, we need to figure out what the coin value is based on the weight. So this is just a very, very simple switch statement where we say if it's between this value and this value, then it's this coin. So not a very extendable, future-friendly thing if you wanted to add more currencies, but for a proof of concept, it works. And then once we know the value of the coin, we can create a deposit entry struct, and we'll use this later when we want to send it up to the server. Cool. So let's take a look at what we built. It's kind of like spaghetti code, but in 3D. So we've hooked up a load cell, we've used an LCD screen, we've used Swifty GPIO to use Swift to work with all of these components. We've also looked at how digital signal works, using analog to digital converters, and we've done a bit of bit banging. That's a slightly prettier picture of it. Cool, so the next part to look at is making the data available from anywhere. So I'm not doing a full talk on Katura. That probably would be an entire talk on its own. I wanted to just give a few kind of highlights and insights into what it's like to use it and how it's really powerful to use it across all the different platforms. So Katura Kit is a client-side framework for sending HTTP requests to a Katura server. Katura and Katura Kit send and receive instances of Swift types directly. So these types can be shared between the client and server. And oh man, it's so much less code. So these are just some short examples of things that we do. So the top one is sending deposit information to the server. And then in the bottom one is how we get the deposits for the Pi and for iOS, getting deposit information from the server. And there's a lot more code involved in getting it to work, but you can just use one type and it all just works quite beautifully, actually. So yes, I would encourage you to have a bit more of a play with server-side Swift if you get the chance. So now we've gone through this smart deposit platform, all powered by Swift. Hopefully you feel like hardware isn't maybe as scary as you thought it was. If you did think it was scary. If you didn't, that's also fine. But maybe you have an idea, but what do you do now? So the first thing you should do is figure out what components you need. There are tons of tutorials online. Most of them are Python. There's nothing wrong with Python, but we should probably write some more Swift stuff. So if you do come across a tutorial that's really helpful, try to write a Swift version of it for the next person. If you want to build something more complicated, it's worth spending a little bit of time learning more about electronics and building circuits. A couple of components, you don't really have to worry too much. But when you get into if you were building like a robot or something where like a person's life was hanging in the balance, you might want to make sure. I've also blown up a Raspberry Pi, only one. I don't recommend it. It's kind of a waste of money. So it's good to learn about circuits more. So debugging. If you enjoy debugging software, you'll really enjoy debugging hardware. Because you don't really know if it's the hardware or the software, and you basically have to resort to making sure you can still make an LED blink, because you don't know if you've plugged the right thing into the right place. But it's much more challenging, but it is really fun, and you kind of have to think about things in a different way. And I feel like I've started writing much simpler code for hardware because I want it to be just like, there's no way that this could be wrong. Because it's more likely that it's a hardware thing with me, usually, because you saw my beautiful skills of wiring things up. Okay, so I want to wrap up by touching on the future of Swift and the community. So I'm assuming that you're all here because you think Swift is great. Yes? Can I get a woo? You're all very excited, cool. But yeah, like we want Swift to be everywhere and used by everyone. Like we don't just want, these like 200 people using it. We want more people using it. And the more people use it, the better the language will be and the more diverse our community will become. Because the world is full of many different types of people in many different types of situations. And if we only have a small subset of people teaching computers how and what to think, the results can be very dangerous. There's lots of examples of this. This is an example of how voice assistants respond to verbal sexual harassment. And it's easy to kind of look at them and think, oh, they're just written as a joke. But really, it normalizes this type of behavior for people. And you can tell by looking at it that the teams that thought this was okay are not diverse teams. They're not people who've experienced sexual harassment. Like, you wouldn't put these kinds of things in. So do we want to enable this kind of technology? Is this the future that we want to create? Do we want to alienate people? Swift is still relatively new, but it's changed a lot over the past few years thanks to the community involvement. And I want you to spend a moment thinking about what do you think Swift will look like in 5 years? Don't just think about the language, but what will the community look like? Who will be sitting next to you at conferences? Where will Swift be used? So I kind of see two futures for Swift. One kind of path that we're currently on. So it's really just like Apple platforms and a few other kind of groups that use Swift. But there's also future two, where Swift is everywhere, used by programmers across many different domains, where it's more popular than Java, which is currently ranked as the most popular language in the world. And this future number one, where it's really just Apple platforms, it doesn't look like we're creating a language or a platform for people other than ourselves. It's not really a good, sustainable future. We should be actively trying to find ways to bring more people in. The barrier to entry for getting into Swift development is quite high, because the cheapest Mac Mini is $800, which I forgot how much that is in pounds. I didn't localize this talk. But that's not affordable for the majority of the world, because you still have to have a screen and a keyboard and a mouse. And yes, you can write stuff on an iPad in playgrounds, but it's not really the same. You can't be a full-time developer with just that. So future two, where everybody's using it, how do we get here? Well, the Raspberry Pi is a pretty good start, because the cheapest one is $5, £5, €5. And you still do need to hook it up to a screen and a keyboard and a mouse. But for $5 for the computer, instead of $800 for the Mac Mini, you have a machine that you can write Swift on. But the tools are a little lacking. So I'm not an expert I haven't tried every single IDE on Linux. The one that I'm using has no code completion, but I can compile and build and run. And there are some people who are actively trying to make some more kind of Swift compatible stuff for Linux. But it's by no means like what it is to just you install Xcode and you're good to go. I was looking at a tutorial yesterday, and it was step 1, step 2, and then it just started going wait, what? And it was just all these terminal commands, and I was somebody who's just learning to code or just wants to learn some Swift is not going to make it past step 2. So we need to do more to help people get onto these more affordable platforms. There's so much that we can do to grow Swift. So I want you to ask yourself, what can you do to help build the community? What tools can you create or contribute to? Who can you teach? What can you do to help Swift evolve? So it's a really exciting time to be working with Swift. Hardware, server side, there's still a lot of really new, unexplored areas to just be a major part of, to improve, tooling and libraries are lacking. So I want to leave you with these two questions. What future do you see for Swift, and what can you do to get us there? Thanks.